chapter of chapter 1, the idea of a secant, right? A secant, and again, the Greeks could do this, right? The Greeks could handle a secant slope. So, let me pause this a second. Okay, all right. Okay, so we've got secant being f of b minus f of a over b minus a, where there's a clear distinction, a clear difference between 2 points, okay? You can see it with your eyes. There's 2 distinct points. And then we talked about, well, the difference between a tangent line and a tangent slope, okay, is now that we're only working with 1 point, and the second point is so infinitesimally close to it that you can't tell the difference with the naked eye, because we call that distance, that difference, h. And h is always approaching what? 0. This was Newton's argument. Okay, so Newton came up with that limit as h approaches 0 of f of x plus h minus f of x over x plus h minus x, which essentially turned the whole denominator. Once he had that denominator set up, the denominator really just became h. Okay, Newton named this the derivative, and he chose the symbol f prime. Okay, that was Newton's notation, and that's how it got published. Okay, and it was called the derivative. We read that as the derivative of the function, or sometimes we say f prime. Okay, with a little, it's not a 1, it's like an apostrophe, it's just a little tick mark. Okay, so here we go. The slope along any single point along a curve is called the derivative. The derivative of the function, okay, here we have. Okay, and again, it just needs you to know that this was Newton. Okay.
Is there going to be like a question about that on the AP test?
They'll say use Newton's method to prove blank, okay? Now, Newton was he was a mathematician, but what is he primarily known for? Science, right? Specifically physics, the whole like an apple falling and gravity and these kind of things, okay? Newton's 3 laws. Sure. So Newton primarily designed his derivative to work on physical problems, okay, which are all mostly polynomial in nature. So this works best on polynomials. And those of you who are in physics and have asked me about the little shortcut for the derivative and stuff, it only works on polynomials because that's what Newton was working on. Okay, Leibniz was thinking on a much grander scale. Okay, Leibniz was able to see that his work was not just limited to the physical realm, but his work could apply to any kind of function. So we'll get to why Leibniz's is a little bit better. Okay, so let's focus on Newton for a minute. Okay, so the tangent slope is going to be f prime. Okay, it is the slope. So if you're writing a tangent line in point slope form, you'll be working with a single point. We call the point A, and we call the point f of A. So those are the x and the y values. The slope is f prime occurring at A. Okay, so remember it is a single point. And point slope form, if you remember from Ham and even from chapter 0 when we did point slope form, that was why I had that on the quiz and the test there. Okay, point slope form was y minus y1 equals mx minus x1. That's point slope form. But instead of the y1 and the x1 and the m, we're going to use these a values. Okay, so where do I put the a? X1. Okay, so a goes here. Okay, where do I put the f of a? Y1, that's the function value. And then the f prime of a is going to go in for m as the derivative. So this is now f prime at a. So you'll hear me say this a lot. If a question is about point slope form, I'm going to say, what two things do you need for a tangent line? And the two things you need are a point and slope. I need a point and a slope. I need to know what point I'm looking at, and then I have to figure out the slope at that point, and then I can write a tangent line. Okay, a normal line. And remember, a tangent line is the one that skims off just like that. Okay, the word normal is not the opposite of abnormal. That's not the way the word normal, one of the meanings of normal. The word normal is synonymous to the word perpendicular. Okay, normal in math means the two things are perpendicular. So if I ask you to create the normal line, that means this red line right here is called the tangent, but the normal will be drawn at a right angle. And so the normal line, and you do your best. It's hard to draw a perpendicular line through something that has a curve that's going through it too. But that would be the normal line because that would be created at right angles. Now, do you remember from geometry and from your other math classes how two perpendicular lines are related in terms of their slope?
Flips and they're
Okay, it's the inverse reciprocal, or the negative opposite, we say the opposite reciprocal value. Okay, so go down to the normal line uses the exact same point. There's no difference in the point. They have the exact same point in common. But what they have different is that we have the negative reciprocal of f prime. So whatever f prime was, then you find the negative reciprocal of that to figure out your point slope equation. So we'll have y minus f of a, which stays the same, but we will have negative 1 over f prime, so that's the opposite reciprocal, and then x minus a. And that is called the normal line. So that's how we define those two things. Okay, so let's do a couple practice ones. Write a tangent line to the parabola when x is negative 1. Okay, write the tangent line. So I would always say, well, what two things do you need? Well, the first thing I need is the point. So I know my point is negative 1 comma something. And then when I evaluate the y value of negative 1, put negative 1 into the function, what do I get? I do. Okay, so the equation is negative 1 for the, or the values are negative 1 for the point. The second thing I need is the slope. The slope is going to require me to figure out what f prime of x is. And so I'm going to need to set up a limit equation to help me figure out what the slope is going to be. So this is what we just ended chapter 1 doing. So if you want to do that in the margins or do that somewhere else, okay, we need to know that what f of negative 1 is. Well, we already know that. And we need to know what negative 1 plus h is so that we can figure out our numerator. So negative 1 plus h would be negative 1 plus h quantity squared plus 2 times negative 1 plus h, and we work that out. So I'll get 1 minus 2h plus h squared minus 2 minus 2h. So overall I have h squared minus 4h minus 1. So then I'm ready to create my numerator, which would have h squared minus 4h minus 1, and then minus the first value, so that would be minus negative 1. And we'll simplify that by simplifying the like terms, which cancel out. So the minus 1 and the minus negative 1 cancel each other out. Factoring will give me h times h minus 4. And then I reduce. And I turn out to have what numerical value?
Negative 4.
Negative 4. Okay, and that is the slope. So the point was negative 1, 1. The slope is negative 4. And then you write your tangent line. So my tangent line will be y minus the y value of the point, which was negative 1, the slope value, which is negative 4, and then x minus the x value of the point. So I have y minus negative 1 equals negative 4 times x minus negative 1. So I can change those to be y plus 1 and x plus 1. You do not have to simplify that. If you do, it's fine, but it's just more work. Okay? You do not have, you can just leave it. Point slope form. Okay?
Can you just go back up? I just want
Up or sideways?
Oh.
What are you,
Previous.
like this one, or you need the
Like
one?
the previous.
This one.
Yeah.
Yep. Okay, any questions on that? Okay, write a tangent line to the same curve when x is 0. Okay, what was the slope last time? Negative 4. Will it ever be negative 4 again?
No.
Okay, no. The slope is going to be different this time. So now I have a different point and a different slope to figure out. So my point this time is 0, comma, and plug 0 in. It'll be 0, 0. And then my slope will be different again. So I set up Newton's method. So Newton's method works great on polynomials. These are polynomials, that's why Newton's method works awesome. And so maybe on the side, you want to figure out, well, what is f of 0 plus h? So that would be 0 plus h quantity squared plus 2 times 0 plus h. So that's h squared plus 2h. So then I can go back to my Newton's formula, and I can take this h squared plus 2h and then subtract the y value of 0, which was the original point value. And I can reduce that by factoring. So h factors out, multiplied by h plus 2. Reduce, plug in 0, I get 2 from my slope. So my slope is now positive 2. So then I write my tangent line using point slope form. So the point slope form is y minus the y value of 0, 2 for the slope, and x minus the x value of 0. So that's my tangent line. You do not have to simplify it. Any equivalent answer is fine. Okay, if you want to simplify that, if you want to write y equals 2x as the simplified answer, you may, but you don't have to. Any equivalent answer is okay. All right, any questions so far? All right, how do we make that a normal line?
You take the f prime of x and you do the negative.
Okay, so remember our tangent line was just y minus 0 equals 2 times x minus 0. Normal lines are super easy because once you have the tangent line, you keep almost everything the same. Y minus 0 and x minus 0, you keep that the same. But to make it normal, you just take the 2 and then you make it the negative reciprocal.
It's for me.
Your phone, I guess? Okay. All right, so any questions on that? Once you have the tangent line, normal line is like piece of cake because you just have to invert and take the opposite sign to your slope. All right, so that worked great for Newton. Now we got to bring in Leibniz. Okay, Leibniz was very, very similar, except with one difference. He didn't use the idea of h. All right, here we go. All right, Leibniz called it a differential instead of a derivative. But again, remember historically, because Newton won the little jury argument thing, they took his word, the derivative, and didn't take Leibniz's word, which was called differential. Okay, but they were meaning the same thing. So Leibniz's notation looks like this. Instead of a prime, Leibniz wrote it like this. He wrote the letter D, which was the differential, and then the letter F to stand for his function, and then he made it a fraction instead of a prime, and then he had the differential of x. And that's going to be actually a much better way to write it. The farther we get in calculus, you're going to see how this is going to be a lot better. His limit idea was not to use h, but to use two separate letters, x and a. So he had f of x minus f of a, and then x minus a. And he said, well, if I want those 2 points to be really close to each other, then I'm going to write it like this, that x approaches a. So just imagine if you have point x over here and you have point a over here, and Leibniz is saying just slide those two till they approach each other, and then you have 1 point instead of 2 points. That was his idea. So Newton was more like, here's point A, and I'm going to make H, and I'm going to put H really close to it, and they're going to be so close that they'll be right on top of each other. Leibniz kind of took a bigger view. So I'm going to start one over here and one over here, and then I'm going to move both of them towards each other, and essentially they'll be approaching, but never right on top of each other, but always approaching super close. Okay, his method works better for rational functions. So think hyperbolas. Inverse squares are rational. Worked better for square roots, or any other roots for that matter. Okay, cube roots. So his, and then when we get to trig, okay, and logs worked better. So Newton's was good, but it was very limited because his focus was how can I use this for my physics and how can I use this for my science, whereas Leibniz was thinking more on a grander scale. All right, so I'm going to show you how, okay, let's write down his name. Leibniz, Leibniz. Gottfried Wilhelm Leibniz. He was German. Okay. So let's use Leibniz's definition to find the derivative of the square root of x, which Newton's, okay, don't get me wrong, Newton's works, but the algebra is much more of a headache. Leibniz's is much more of an elegant solution. All right, so to tell the reader, to tell the grader that you're planning to use Leibniz, you use this notation, okay? It's basically an announcement. I plan to use Leibniz's notation instead of the prime notation. If your prime is for Newton, Leibniz would be for this. All right, my limit is going to have x approaching a. My denominator will have x minus a. Can x ever be a?
No,
Why not?
because then they would be right on top of each other.
Okay, but what would happen mathematically if x and a were the same?
0.
I get 0 in the denominator, which I can't have, so it can approach, but not. All right, so what we do here is, okay, I want to have f of x, which I already know is square root x, and then I want to have f of a, which is the square root of a. Okay, and here's where the elegance of the algebra comes into play. Okay, the square root of x minus the square root of a needs something called, and you've learned this before, something called a conjugate. All right, so let me give you an example of two values that are conjugates. All right, x minus 3, x plus 3. Those are called conjugates to each other. You saw them in imaginary numbers too. We would see a plus bi, and then we would see a minus bi. Those are called conjugates, okay? Conjugates are super elegant when they get multiplied together. So this one, the elegance is going to be when we bring the conjugate into the problem. And we're going to bring the conjugate in of the thing that's more complicated, which is the square root one. So we're going to bring in, I'm going to multiply this by the conjugate, the square root of x plus the square root of a. But if I multiply the top by the square root of x plus the square root of a, what else do I have to do? I have to multiply the bottom. Okay, and now we're going to FOIL. And you might think this doesn't look very elegant to me, okay? But everything's going to drop out, and we're going to have something really beautiful left at the end. Okay, so we'll work this out a little bit. So when we FOIL the numerator, so I'm going to make it long enough that I can handle it. Okay, so what's the first part? Rad x times rad x. X, okay. What's the second part? Rad x times rad a. Positive rad xa. Okay, and then minus the inside part. Minus rad x rad a. And then the last part.
A.
Minus rad a times itself is going to be a. Okay, the bottom we are not going to bother to FOIL. Okay, leave the bottom unfoiled. You'll see why in just a second, if you don't already. Okay, what happens elegantly in the numerator? Okay, I can cancel out the x minus a with the other the rad x minus a with the other rad x minus a. And so what I'm left with, oh, isn't that nice? X minus a by itself on the top, which I also happen to have in the denominator. And then I have rad x and rad a also in the denominator. So the elegance happens not only do the terms cancel in the numerator, but now I also have an opportunity to reduce the denominator. And x was, now I can plug in that x is approaching a. And so I can plug in the value, which means I don't, so I have 1 left in the numerator because I reduced, and you're always left with a numerator of 1 then. And then as x approaches a, or a approaches x, they're approaching each other, I end up with the rad of x plus the rad of x, which doesn't make 0. It makes 1 over what? 2 rad x. Same thing. It's all, their x and a are the same thing. They're approaching each other. It's fine. You can totally do a's if you want. Does not matter. X and a are approaching each other. If you like it that way, that's fine. Okay, because of it, essentially x and a are getting to be the same value. Okay? So again, this is Leibniz's definition. Okay, what can we use this to tell us? The slope along what original curve?
Rad x.
The slope along rad x anywhere. Anywhere along rad x. Find 17. Okay, well then what's the slope there? 1 over 2 rad 17. Okay, if I want to know the slope at 25, who can tell me the slope at 25?
1 over 2 rad.
You can do that. 1 over 2 rad 25. What's that?
1 over 10.
1/10. Okay, the slope is 1/10. Okay, at any value. Yeah.
So do you not have to like rationalize that?
No, we don't have to rationalize it. No, any equivalent answer. Okay, any equivalent answer. All right. Find the derivative and use it to write a tangent line. Okay, which method would you use for this?
Newton.
Okay, Newton would be an elegant method to use because it's a parabola. Now we've done enough Newton. I think we're okay. Let's move on. I would like to do a hyperbola with you instead. Okay, this says find the normal line. So we're going to need, what, 2 things? A point, and we're going to need a slope. Let's find the slope first. And when we're finding the slope, we're going to be finding the slope of the tangent. And then we're going to have to make it a normal. Okay, but let's do, and because this is a hyperbola, let's do df dx. So this will be the limit as x approaches a. Denominator is x minus a. We start with f of x, which is 2 over x, minus f of a, which is 2 over a. Okay, so then the algebra on this. I'm going to encourage you, because has multiple fractions in it, to think of it this way, to 2 over x minus 2 over a. Instead of dividing by 1 over x minus a, let's do what instead? Multiply by the reciprocal of x minus a. Okay, now, I'm holding. I didn't change anything, I just moved it from a division problem to a multiplication problem. Okay, let's focus on this part of this. What's needed to subtract two things? Common denominator. How do I get a common denominator? Well, what do I have to multiply the 2 over x by? A on the top, a on the bottom. What do I have to multiply the 2 over a by? X on the top, x on the bottom. Okay, so that will give me 2a minus 2x over the common denominator, ax, or xa. I don't care how you write it. And then still multiplied by that 1 over x minus a. Now I need to factor. Okay, what can I factor out that's common? The number 2. So that's going to give me 2 times the quantity, a minus x, over the denominator, ax, times that 1 over x minus a. Now usually factoring is done so that you can reduce. Is there anything I can reduce here? And I'm going to say yes.
Yes. That multiplying the ax. Wait, no.
Okay.
That's not.
All right. I can factor this term with that term. Now, if they were both the same, what would they reduce to? 1. But these are opposites. So what do they reduce to? Negative 1. So I can reduce them, and they reduce to negative 1. So what is my That's what opposites do. These are not conjugates, they are opposites, right? These are conjugates because the order stayed the same. Opposites are when the order is different. Okay, so what's my numerator? Negative 2. What's my denominator? ax. And now I can plug in x approaching a, and you could say either a squared if you wanted, or you could say x squared. And well, I would accept either because a and x are approaching each other and they'd be the same thing. Okay, now we just need our point and we need our slope. Our point at the number 1, how do I find the y value for that? Plug in 1 where? In the original function, which gives me 2. And then my slope, I plug in 1, but plug it in where? Into the Leibniz's definition of derivative, and what do I get? Negative 2, and now I want to write the normal line. Normal line. So it'll be y minus the positive value of 2, and what's going to go in for the slope? Positive 1/2.
So wait, I have a question.
Yeah.
Could you have flipped the slope and then plugged in 1 and still gotten that 1/2 and just plugging 1/2?
Sure.
What is the point of the normal line? What does that do?
Oh, can you give me a pass on that to answer that? That's going to take a little bit longer for me to answer on that. Okay. So last thing we want to talk about. Yeah, sorry.
For the slope, you plug the x value into that final
Yes.
derivative?
Yes.
Okay.
So we were plugging the x value in 2 places. You plug the 1 in here to get your point, but you plug the 1 in here to get your slope. But that's a tangent slope, not a normal slope.
And then you take
All right.
It's just the time of day.
Now, somebody, I forget who, one of you accidentally submitted your physics homework to my class. Is that you? Okay, so I saw what you were doing, and you were looking at graphs like this, and you were turning them, which is exactly what we're talking about here. Okay? All right. So again, this is, because they're all linear pieces, this is easier for us to figure out. All right, this graph here is continuous. All right, when we, graph the derivative of it, it will no longer be continuous. Okay, what is this? There will be three pieces. Why? Because there are three sections of this graph, each with a different slope. Okay, each of these sections is going to be graphed into a derivative based on what its slope value is. All right, what is the slope value here? 1. 1. How many, what's the interval length that happened? From -4 to -1 with a value of 1. So we draw from -4 to -1, we draw a value of 1, which is right here. Okay? The end is an open because that was the beginning. This one is, closed. And then the open is where the connection, like the corner, is happening. Okay, the next section of the graph here lasts from -1 to +2. And what is the value of that slope?
0.
0. So from the corresponding -1 to +2, I draw a value of 0, which is right on the x-axis. So I'm going to draw it a little bit above so we can see. And that starts with an open circle and ends with an open circle because there were two corners on either end. And the final section of the graph only lasts from 2 to 4, but what kind of a slope does it have?
-2.
Okay, down 2 over 1 or -2. So then from 2 to 4, I'm drawing a value of -2 and I end with a closed circle. Okay? So this is called the graph of the derivative. The value of the derivative are just the individual integer values from the slope. Okay, so this was slope of 3. This was slope of 0. And this was slope of -2.
First one, wasn't that a slope of 1?
Oh, sorry, slope of 1, it was an interval of 3. And then we turn those numbers, those integers, into a corresponding derivative graph. All right, the thing is, can you go backwards?
100%.
Okay, can you go backwards? Okay, so this one has a value of what integer? No, the one I'm drawing right on. This one has a value of 1, which means the thing that you draw should have a slope of 1. Okay, and this one has a value of -1, which means the thing you draw should have a value of -1. Okay, so something with a value of 1, I'll start with anything. This one has a value of a slope of 1. And this has a value of a slope of -1. Now, those are not in the right places yet. I need to make sure those pieces, which have the right slope, but they're in the wrong position. It says they have to go through 0, 4. And it says it has to be what kind of a function?
Continuous.
Which means the pieces need to do what? They need to
jump.
connect to each other because they're continuous. So I need to make sure that pieces that are shaped like that go through the point 0, 4. So I'm going to have a slope of 1 that way, and I'll have a slope of -1 this way. And what kind of a shape did we just create? We did. We just created an absolute value graph. Okay? So you can use your notability to like drag the pieces to the right places once you know what the pieces are supposed to be. Okay? All right. Any